Welcome back. So this is our final video. Hopefully, we'll have two examples here for 8.5. So here's our new problem, and again, this is doesn't look good for any other techniques. Use substitution, integration by parts, trig powers, trig substitution, any of that. So, but the denominator is actually not factorable, but it's already factored. This part here can't. I wanted to make that yellow. It can't, that part there can't be factored. As much as you want to try to factor it, signs just don't work it out. So we're going to jump right into partial fraction decomposition. It's already in a factored state. But there's something unusual about this part. It's a quadratic. That's not, that we can't factor any longer. So that's gonna be why we're going to call this type 3. And type 3 is when you have a irreducible quadratic term. So that x squared minus 2x plus 3 is a quadratic term that cannot be reduced. So let's go to the partial fraction decomposition and see what that means. We did do this in pre-calc. So it shouldn't be, it might come back to you. So you think, well, all right, I guess I'll put one of my factor terms under here and my other factor term under here. But you might recall that I said the numerator in these is always 1 degree less than the denominator, so this should be just a. Now the exception, I didn't mention it at the end of the last video, is at the repeated factors. They kind of violate that rule. If you have a repeated factor, even though it may be squared below, it's still going to be constant up top if it's a squared linear factor, okay? Because it's a repeated linear factor, so it's 1 degree. This is a quadratic term, so it's going to be 1 degree less, so it's going to be first degree. Well, first degree equation looks like this, right? Like f of x equals ax plus b, or you might like mx plus b, or something like that. So what letters should we use? Should we use A and B, M and B? Well, we've already used A, and we like this capital letter thing. Let's just keep going with the alphabet as BX plus C. That is a linear expression, which is 1 less than quadratic, which is below. That's what you always have to do in type 3 and in type 4. So be ready to write the kind of BX plus C thing if the denominator is not reducible. It's an irreducible quadratic. Same thing happens here. You multiply everybody by the common denominator. X plus 1, x squared minus 2x plus 3. And this is just really tedious, writing this down, but it helps us not make mistakes as often. Okay. Done all that, we can proceed. So we have x squared minus 4x plus 7 equals a times a whole quadratic. That's going to be hard to work with. And then what's wrong with this? I'm going to make a mistake here. I just totally disrespected the bx. It's not bx plus c times that. Bx plus c all is times the x plus 1. So you must have parentheses. Okay, so usually what we've done at this point is we look for that perfect number, that number that will destroy all but one letter. There is a single perfect number, and I am the advocate of using as many perfect numbers as you have given to you. There is a technique we're going to need to do on this one, but I'm going to use it at last resort only. So x equals what would be our perfect number? -1. And I will say something about that here in just a second. Just going to plug it in everywhere first. Why -1? Because it makes that 0. And if that's gone, the whole thing is gone. So you're looking for something that will destroy all but one letter. So this becomes what? 12? And this becomes 6a. 1, 4, 6, yep. So a is 2. Hey, we got 1. but there are not any more perfect numbers. There's nothing that can make a go away, in fact. Although if you pick 0, I'll tell you, and you plug in 2 for a, you could figure it out, okay? You could do that. But try it if you want. But I want to show you this type 3 move. We did this last year. I call it the coefficient match. And I think I've told you before, some people watching this video are probably thinking the same thing, always do coefficient match in all cases. I'm a fan of using what I call perfect numbers if possible, but coefficient match is pretty cool. Often more work, especially if you don't pick up the easy ones. So let me show what I mean. So when you get stuck here, let's just fill in what we know. We know this is 2. And while we're at it, why don't we go ahead and distribute? I'm just going to do this. Make life a little easier on ourselves. 2x squared minus 4x plus 6. And the rest of this would be, I'm going to distribute from there. Bx squared plus bx plus cx plus c. Okay, so what we're going to do is match up the coefficients. Really a fun idea. And it says if 2 expressions are equal, like a couple polynomials, then all of their terms must be the same. They must have the same linear term, the same constant term, the same quadratic, cubic, quartic. On the way up, they must all be the same. So let's see what we got here. Oops. So if I match these up, I'm going to combine like terms. I have a 2x squared and a bx squared. I have 2 x squared terms. So I'm going to do something kind of unusual. I'm going to factor the x squared out of those 2 and put it on the right end. That's weird, huh? So I have 2 plus b x squareds. You know, if the b was like 7, it'd be 9x squared, right? When you combine them, because 2 plus 7 is 9. So it's 2 plus b x squareds. Let's see how many x's I have. I have a minus 4x, a bx, a cx. I'm going to do the same thing with these. I'm going to factor the x out of those 3 and put the coefficients in the parentheses. Negative 4 plus b plus c. And then finally, my constants. I have a 6 and a c, and I'm going to do something unusual there too. I'm going to put them in parentheses. That's just weird, right? But the reason I'm doing this is to show you this technique, hopefully more clearly, the coefficient match. So here's the x squared term, here's the x squared term. For these to be equal, the x squared terms must be equal, the linear terms must be equal, and the constant terms must be equal. So what does that mean? That means that the coefficient here is 1. 1 must equal 2 plus b. Got that? If they're equal, the coefficients of the quadratic terms must be equal. Negative 4, the coefficient here, must be equal to negative 4 plus b plus c. And finally, 7 must equal the constant here. 7 equals 6 plus c. So what I do is I solve the ones that look the easiest first. Well, yeah, c is 1. And here, b is negative 1. And then usually there's more information. You don't have to do anything with that, but it might be nice to go in and just test it out and see if it works. It does work. If that's true, you probably did it correctly. So we've done it. We found A, we found B, we found C. So after all that, we can plug that back in as our integral. Well, let's write our summary statement here. We learned that x squared minus 4x plus 7 over x plus 1 times x squared minus 2x plus 3. We learned that that can be written as 2 over x plus 1 plus negative 1x plus 1 over x squared minus 2x plus 3. It's kind of awkward, negative 1x. I could fix that a little bit. So now we're going to integrate that part and see if that's a little easier. So the integral of 2 over x plus 1, no problem there, plus, let's call this negative x plus 1, a little bit more normal way of writing it. Okay, well, the idea there was that that's supposed to make it easier. Well, the first integral is doable, right? It's just 2 natural log of x plus 1. But what do we do with the other one? We can't do partial fraction decomposition again because that denominator is not factorable. Maybe a U substitution, would that work? Are things primed and ready? In the beginning, at the beginning, it wasn't, we had too much going on to U substitution. Maybe it would work now. Let's see. Because the numerator is 1 degree less than denominator. So that would be our U. Our du would be 2x minus 2. Can I make 2x minus 2 equal negative x plus 1? What if I divided everything by 2? What if I multiplied by negative 1? And we are there. Negative x plus 1. That can be plugged in. That can be plugged in. So this becomes plus, let's put that negative 1/2 right away, minus 1/2, integral of, all of this is crunches down to 1 over u du. So the 1/2 was from the du. Okay, let's get back to, so we have 2 natural log x plus 1 minus 1/2 natural log of u plus c, and finally plugging back in for u, 1/2 natural log of x squared minus 2x plus 3, and that's what I got. Did it. I feel like that was pretty long. I'm gonna actually, we'll keep going. We'll press on, get our next one done. Hopefully that makes sense. That type 3 move, you're gonna see that again in our type 4 problem coming up. So let's do our last one. Okay, last one, example D is the integral of x squared minus x plus 9 over x squared plus 9 quantity squared dx. Okay, I kind of made it a little easy on us here, and that the denominator is clearly not factorable. X squared minus 9 would be factorable, but not x squared plus 9. And it's squared, so this is a repeated quadratic factor. And when I say quadratic, it's kind of implied it's not reducible. So I guess I could say repeated irreducible quadratic factor, but repeated quadratic factor. We did not do this, at least in my pre-calc class. It's in the textbook, but we did not do it. And there's really no real surprise here. It's a type 1, type 2, type 3 combination, because you have the repeated and you have the irreducible quadratic. So let's take a look at what would happen here. And this one's really not too bad or too long. So we're gonna have to write x squared plus 9. Now if we just did that, it's not gonna have that denominator. So we have to have at least 2. There's no, you would never do this technique and not have 2 parts. That would be kind of pointless. So we're gonna have 2 parts. 1 part with the square and 1 without. That's type 2 like. Up top we have ax plus b on this one, and this will have cx plus d. So since these are irreducible quadratic factors, quadratic terms, you put 1 degree less up top. On the right term, it's 1 degree less than the thing in the parentheses. Okay, then we multiply that out. So everybody's getting multiplied by x squared plus 9 quantity squared. Something kind of peculiar is going to happen on this last term. The whole thing's gone. So we'll see what happens there. X squared minus x plus 9 equals ax plus b, and x squared minus 9. Hopefully you realize I got to put that in parentheses. And this is just cx plus d times 1. So there's really no parentheses needed. Is there a perfect number here? I don't think so. So we're going to go right to coefficient match. So FOIL this out, ax cubed plus, I'm going to put them in order and do the inside next. Okay, and then we will collect our like terms. No one goes with the cubic term. That's weird. There's not even a cubic term on the left. What are we going to do about that? We'll see. The squared terms, oh, only one of those. That one's accounted for. And then the linear terms, I have two of those. I have a 9a and a c. And then our constant terms, you don't really have to put them in parentheses. I like kind of the organization of seeing it really clear where they're all in parentheses. So right away, what's a? There's no cubic term. A 0. B 1, right? Matches up with that. 9a plus c is -1, but didn't we say a was 0? So c is -1. And then 9b plus d is 9. And we've already established that b is 1. So d is 0. Yes, that looks right. So what we've learned is that x squared minus x plus 9 over x squared plus 9 quantity squared is simply 1, well, let's just write out 0x plus 1 over x squared plus 9. That's a 0. Plus negative x, negative 1x, I guess we'll say, plus 0 over that. Okay, let's put it into our integral. So we have the integral of, we could just call that 1 over x squared plus 9. And we'll call this minus x over x squared plus 9 quantity squared dx. There we go. So to integrate this, we have a couple of different strategies that are necessary. The first one, I'm going to just kind of split this up. I'm going to leave that blank for a moment. And we have that. What could I write here instead of 9? About 3 squared. Does that hopefully jog your memory that this is, we haven't even seen this in a while, but this is the arc. This is the arc tangent, so we do need the 1/3 out front. Yep, let's do our match here. I should have done that. So with the match, we see that a is 3, u is x, and du is dx. Everybody matches up and is ready to go. So it's 1 over a, 1/3, arc, tangent, and then x over 3. What about this other part? We can't do arc trig or anything, but this is just a good old-fashioned u substitution where u is that, therefore d is 1 degree less. Right? We'll use that, Of course, there's a square down there, but we can handle that. So let's just move that 1/2 out front. So this is just going to be u squared. And that's the same thing as, let's rewrite this. Don't have to show this step, but it might make it a little easier. You see, oh yeah, that's just going to be -1/2. This goes to the -1. Put a -1 there. Or finally, this becomes plus, and you could put a 1 up top and then 2u down below. I guess I'll take my time and do one more step here. And then you could plug in for u, and we are done. Plus 1 over 2 times x squared plus 9.